Good afternoon, everybody. My name is Venkatesh Choppella, and my talk is about a small language for tensor combinations and its type systems. So in this talk, tensors are synonymous with multidimensional arrays, and tensor combinations are synonymous with expressions that do not involve index variables. So what is the motivation for this? There's been a lot of interest recently in renewed interest, if I may, on analysis of arrays and tensors and so on, of course, within the context of data-intensive programming, machine learning, and so on. So my talk will motivate the reason for considering such a language and get into the technical details of this language. In fact, we present 3 languages and discuss the types and semantics, and then transformations to these combinator forms. Okay, so what we're really after are expressions that do not have index variables. Normally we're used to seeing array expressions with indices. So one might ask, is it actually even possible to do that? Well, there's been a rich history of examining various forms of notations, combinatory logic, De Bruijn notation, and so on, which try to eschew the use of variables. Okay. So just to give you an example, let's start with what we're all familiar with, which are array expressions or tensor expressions, if you will, that involve variable indices. So the j, I, j, and k here are all indices, and the other things here are the array identifiers A and capital A and B, and there are some operators like plus, multiplication, and the sigma summation operation. We're going to consider a language purely of expressions. There are no sequence statements, no assignments, no if, and no explicit loops or function extractions. We're also going to assume that these expressions are all untyped. That means all the indices have the same type, the same range, and those ranges are all assumed fixed. Okay, so the whole idea is to express a for loop as an expression that involves some kind of free variables in the index, free index variables. Okay, so what we're really after is this thing that I call factorization. You have an expression on the left-hand side, which is your familiar array expression that I'm going to call scalar expressions. And these expressions on the right-hand side are, you can see, divided into 2 parts. Okay. There's the variables, the index variables on one side, the right-hand side, and preceded by these other expressions. You can think of these expressions as denoting functions over these index variables, indices. Okay, and just to give you the first example, aij doesn't have to be transformed, it's just aij. The second one, notice how there's a selector that selects 1, 1, that is ii, from the index set or index sequence ij. Okay, that's called a selector, and the little list here 1, 1 is a sequence of positive integers. It's called a posec for short, and that posec determines which elements get selected from the sequence of indices. Okay, we also in the array in the scalar language we have the summation operation, and when you move to this other representation, the factorized representation, that is replaced by a contraction, which notice there is no index here for the contraction. Okay, so how is this done? What is the language in which all of this happens? What are the transformations? Is there a type system that can control somehow what these expressions mean, and so on? That's what the rest of the talk is about. Okay, so the way we're going to solve this problem is we're going to define a scalar language, L underscore, which has array references with index variables and operations and summation. And then we look at a variable free language, L hat, that uses these selectors. And then we consider a hybrid language that has both of these, and we define a type system on this hybrid language, and this hybrid language sort of subsumes both L hat and L underscore. We define an equational rewrite system that lets you go either towards L hat or towards L underscore. That's the plan for this work. Okay. Of course, there are many other things we have not explored yet, but we do plan to explore. We want obviously index ranges, dependencies on the indices, arithmetic, tiling, and so on and so forth, which are the standard fare of any decent compiler for arrays. We want to translate code, C++ code into this variable-free expressions, and we would like to see how compiler transformations can be expressed in this language. Okay, so let's get to the key element of this whole exercise, and that is this operation called selection. Okay, so in this example above here, look at this expression sigma j aij times bjkl. Okay, this is the one on the left hand side is in the scalar language, but if you want to promote this whole expression into a language in L hat, okay, the E is supposed to be in L hat, because we need to figure out what is E, and this is a factorized form. All the indices are moved to the right, and E needs to be an expression in L hat. Okay, so what is this language L hat, and what is its semantics? What does E mean? Well, you can just by looking at this expression say that E has a dimension of 3. Okay, so how do we compute what the dimension of E is, and what is the language in which this is all discussed? Okay, so by the way, E is an expression like this, and this is a solution we will arrive at. We will show a small derivation of how you get from the left hand side to the right hand side. Okay, and of course we need to find out in what sense these transformations are kind of correct and so on. Those are of course questions we will need to address. Okay, so just getting into the machinery now of how these selectors work. I briefly talked about these things called POSEX, a sequence of positive integers. So here's just examples of sequences of positive integers. Okay, and these sequences get there are two properties. We need to know what is the maximum in the sequence and what is the length of the sequence. If the sequence is empty, the maximum is 0. Okay, so once you have a POSEC, the POSEC can define a selector. So a selector is parameterized on this POSEC. So for example, here, let me just give me a second here. Yeah, here the POSEC is empty, so the result is always going to be empty, and you can pass a list of any length. Here the POSEC is 3, 1. The selector that you get out of that takes a list of at least size 3, and then the POSEC gets into action, just picks the elements that it's specified, and here you pick the third and the first element, which is y and w. Okay, so again, the constraint is that if you're applying the selector on something, the length of that thing should be at least equal to the maximum element in the POSEC that is defining the selector. Okay, let's move on. So all of this is captured now by a type system, a very simple set of rules that let you look at that kind of are able to figure out what are the constraints on the dimensions of what are these selectors, what are they actually doing. So if you think of a selector, it takes a list of length m and returns a list of length n. Okay, what is the m? And of course the selector is parameterized on this s. What is the relation between the s, the m, and the n? That's given by the selector rule. And what is this capital SMN? That is nothing but the signature of the selector. What is the maximum value in it, and what its length? What is its length? Similarly, there is a rule. Remember that we said you could pass a list of any size, and then you can pass that. So you can kind of, there's a subtyping rule, and you can promote the type of the selector and then apply it to a list. So when you apply it, it's just like the application rule, LM to N, and the list is of size LM. So the result here should be sigma of Q should be Ln. Okay, and so on and so forth. Okay, so with this background on these selectors, let's look at what the syntax of these languages is. So this scalar language we're all familiar with. It has array references. That's the array. Small a stands for array identifiers, and that is the sequence of references. There's all letters. Here we're just assuming they are all variables, they're not constants. There are primitive operations, and there's this summation. And notice there's an index when you do the summation. Okay, so let's look at now this language L hat, where in L hat you have not array references but simply array identifiers. So the references are missing, and of course you have primitive operators. So these operators are sort of like plus and multiplication. They're promoted now to work on E hat expressions. And notice now there's a select operator, okay, whose semantics will be described in terms of the sigma, and the select operator is parameterized on this list of positives, which is a vector, and the select works on an E hat. There is also a contraction which matches the summation, but notice there is no index here. That's not a typo. There's no index over there. Okay, so let's now consider a hybrid language. The point of these two languages are these two languages form kind of the endpoints in the space of expressions, and both are of interest. The first one is what we're the L underscore language, which we are used to dealing with, and the L hat is where we want to go with this factorization. Okay, so this is just a language that has array identifiers, index references, primitives, selection, summation, and contraction. We're going to look at examples of all of these. Okay, so let's just take a quick example. These are of various types of expressions in L. If you look at this one particular one in red, okay, there's clearly something wrong with it. The types don't match, so you need to be sensitive about. So you need some kind of type checking and a type system in order to be able to catch things like this. So let's look at the types in semantics. We're motivated by trying to locate expressions that don't have a meaning, that are not meaningful. And the meaning here is nothing but the dimension. So every expression, if it's well typed, will denote an array function, and an array function of dimension n. That means it takes n indices and gives you a scalar. So that's what we're after. So let's construct a type system here. We have judgments. The way to read this is E is well typed with dimension n in the dimension environment G. Okay. So what is G? G simply maps identifiers to their dimensions, and E is an expression in L, and n is supposed to be its dimension, which is a natural number. Here are the type rules for L. Okay, I won't go into these details. I will skip over all the details, just point out a couple of things here. The first one is sort of easy to understand. If you have the identifier A and it's mapped to n in this environment G, then the type, the dimension of small a is just n. Similarly, you've got other rules like op. If the operands all have dimension m, and then you build kind of another function, a higher function, which just takes all of these and gives you also something of dimension m. Okay, so you can think of mapping like a plus, aij plus bij, and you're looking at removing the, so you want to turn that into a plus b, and you want the same dimension. Notice the moment you do a reference, the dimensions all go to 0. And such is also the case for sigma, the summation. So summation is clearly in the scalar language L underscore, so that's the rule for summation. On the other hand, the other rule for contraction, the contraction actually changes the dimension. If you see with the sigma, the dimension is n, without the sigma, the dimension is n plus 1. So that's contraction. The select rule looks a little complicated, but what the select rule is trying to say is the selector comes in the way and allows this expression to take more indices, very roughly speaking. We'll see an example of that. Okay, so here's a simple derivation, and look at the last line here. The last line says we are trying to derive a type for the select 1 to a multiplied by select 2 3b ijk. We want the type of that to be 0. Okay, well, if the type of that is going to be 0, so notice this is a factorized expression because everything on the left hand side is an L hat, and this is a linear sequence. That means there are no repetitions of indices. Okay, so if you work your way through the type system, you end up at this point where the type, the dimension of select 1 to a is 3. And how did we get that? Well, if you look at the dimension environment G, A has a dimension of 2. Okay, and if you look at the selector 1 2, its maximum value is 2, its length is 2. And when you apply the selector to A, remember what you're getting back is another array function that can take at least 2 elements, at least 2 index variables. So which means it can take 3 as well. So we put the judgment 3, which is sound with respect to this type system, which is valid, and then we kind of work out the proof. The idea here is that when you go from we want to filter out these well-typed expressions in L, and that's the type system we want to use, because it's only these well-typed expressions in L that we can give a semantics to. Okay. And what is that semantics? A well-typed expression with dimension n corresponds to an array function. The static semantics is the type system. In the dynamic semantics, which we won't go into the details, we take a dynamic environment and a compatible static environment, a well-typed expression of dimension n, and map it to an array function of dimension n in this space. Okay, so now let's focus on the transformations. So what do we have right now? We have a language L and 2 subsets, if you will, L underscore L and L hat. And we want to be able to take an expression and put it in this factorized form, or we want to either convert it into a scalar form. Okay. So what is now we are ready to define what a factorized form is. A factorized form, an expression in L is factorized if it is well typed, and if it is of the form E, where E is an expression in L hat, and a sequence of indices which are linear. That means there are no duplicates, right? So now you can see the factorization. That's what we mean by factorization. You split it into 2 parts. Okay, and similarly with scalar form, an expression is in scalar form if it is well typed and belongs to L underscore, which means it has none of these selectors in it. Okay, and it has summations, but the summations have indices, and has array references. Okay, so what is factorization? It's a process of transforming a well-typed L expression into factorized form, and scalarization is transforming it into a scalar form. Okay, so here are the rules for transformation. The rules for transformation, there's one pair of rules for each construct here: select construct, the arithmetic operations, and the summation. Okay, the rules on the left correspond to expressions that are in L, and when you go from those expressions to the right, notice that you're moving towards L hat because you're introducing these selectors and you're doing this factorization. Notice so basically these are all left associative. So what we are really saying is that. Okay, and similarly here we're doing that. Okay, so let's see how these transformation rules work with a simple example. So here's the example that we had in the motivation section: sigma j aij times bjkl, and we want to eventually convert this expression into a factorized form. The blue is indicating that you're converting this expression incrementally into factorized form. The underline tells you the regex, and the blue tells you what it gets converted to. And you can actually read this backwards as well. So you can start with the blue and end up with the gray, which is a scalar form. So this is a scalar form, and this is the factorized form. Okay, so you can work out the details of these. This is just to show how you introduce the select operators. Let's just look at a very, very simple part of this. There's bjkl, okay, and now you want to move this, you want to write this in such a way so that the indices are all shared. So you need to sort of bring in the I. You bring in the I here, and notice you need to have j to be the first one because the sigma is happening over j, and you sort of insert the I here, and now you need to select bjkl out of that. So you pick 1, 3, and 4. That's the intuition for selectors. Okay, so there's more work pending, of course. We want to make sure there's type preservation, there's semantics preservation. How do we know these rules are sufficient? How do we know these rules give you the right the confluence is true, and how do you know there's a unique normal form. All of these details are to be worked out. We've started off with a simple initial prototype in Haskell to implement all of this stuff, but there's more work to do. So in summary, we've got an index-free notation for tensors. Select, everything is driven by select. The select actually is a very interesting operator. You can put lots of things inside it, which is what we're hoping to explore. And we've got a type system, and we've got transformations. Okay, I'll very quickly discuss related work. The related work can be categorized into two parts, sort of like this, if you will. Okay. On the left-hand side, you see mostly papers that deal with these typed intermediate representations. So the type systems and typing is very important for them. And a lot of stuff is driven by the types. In fact, the most interesting paper and closest to our work is this paper on type-safe imperative tensor intermediate language, which also has higher order operators and a variable free notation, but doesn't use selectors, has other operators. On the other hand, you have these generalized tensor algebra papers dealing with tensor algebras that are implemented. Again, the one that's relevant is this PLDI paper that talks about, it has explicit index variables, but it talks about sparse arrays, which is also of interest to us because we'd like to know how to represent sparsity and so on. Okay, let me conclude by saying that we are proposing here an alternative syntax for array expressions. Ours is not the first attempt at that. There have been multiple attempts, but we are introducing the selection operators. Okay, there's future work to, as I said earlier, to look at index arithmetic, dependencies, styling, and so on. And hopefully we can see how these can work with state-of-the-art compilers. Let me conclude here by acknowledging the help I got from my other students at Hyderabad for several discussions. Thank you very much. I'll be happy to take questions in the question hour.